Hey everyone, this is Igor and Jonathan. We're Team Omega, and this is our final project for EEC 201, Speaker Recognition Project.
All right, so first, I'll talk about speech feature extraction. So when we read the signals in, we want to clean them up a little bit. So the first step we do is we do mean normalization on the signals. So as you can see in this example of SO9.wave, some signals have a DC offset, which messes up our feature detection later on. So we want to get rid of this DC offset, and we subtract the mean of the signal to get rid of this DC offset. And then the next thing we do to clean up our signals is we normalize the amplitudes to be between -1 and 1. So as you can see in this example, some speakers speak louder and some speakers speak quietly. So that translates to the signal amplitudes being higher for some signals and much lower for others. So after we normalize them, the word detection that we do later on will be less sensitive to these amplitude variations. So the next thing we do is we detect the word part of the signal. So the overall signal contains quiet parts, and then the part of interest, which is the word part. So what we do is we split the signal into multiple frames, and then look at the PSD of each frame and the average power of that frame. And then once the average power exceeds a certain threshold, we determine that to be the start of the word, and then collect the next n amount of samples as the word. So we used a threshold of about -45 dB to determine the start of the word, and then we used 500 milliseconds as the amount of time to collect for the word. As you can see, in this example, the speaker spoke faster, so there was a little bit of the silent part captured with the word as well. However, other speakers take longer to speak, so there would not be a quiet part. And on average, we found that a length of 500 milliseconds was about the average time it took for the speakers to say the word. So, back up. Okay. So the next thing we do is we calculate the mil frequency Kepstrom coefficients on the cleaned up data. And that consists of 4 different steps. So first we do the short time Fourier transform, or the STFT. Then we pass the signals through a mel-spaced filter bank. Then we calculate the Kepstrom, and lastly we normalize the values. So first we calculate the STFT of the signal by splitting up the signal into multiple frames, doing an FFT on each frame, and then estimating the PSD of each frame. So the idea is within your window, the part of the word should be quasi-stationary, so you can look at some spectral features of that frame. And we used a 25 millisecond window with a 15 millisecond overlap of each window to get a good estimate of spectral features within each frame. And then the next thing we do is we pass the signals through a mel-spaced filter bank. So the mel-spaced filter bank kind of models how humans perceive sounds, where lower frequency banks are spaced linearly apart, and then higher frequency banks are spaced logarithmically apart. We used 40 banks to get a finer frequency resolution. And then to effectively filter the signals through this filter bank, we multiplied the STFT output with the filter banks. And here's the output of the filter banks. And then after we pass the signals through the multi-space filter banks, we calculate the cepstrum of each frame. As you can see, most of the energy is contained within the lower cepstrum coefficients. So we select a range of the cepstrum coefficients that we're going to use as the MFCC coefficients, and we determined after a few trials to use coefficients 2 through 14 as our MFCC coefficients. And then lastly, we saw that some coefficients have outliers that kind of skew the coefficients in the wrong direction. So we did mean normalization on the coefficients to reduce the skew. And then also we wanted to limit the range of our coefficient values to be between -1 and 1. So we divided the coefficient values by the L infinity norm to get them within the range of -1 to 1.
All right, so now I'm going to talk about the speech feature matching, I should say. So to accomplish the speech feature matching, we used an algorithm, what is known as the Linde-Buzo-Gray. This comes from an IEEE paper, and it's commonly referred to as LBG. And the idea behind this algorithm is to take these MFCCs, which we generated from the audio, and to store it in a feature space and find code words which make up a code book depending for every training vector coming in that best matches these MFCCs in the feature space. And that way we can kind of identify unique features between training vector to training vector, which is also speaker to speaker, and be able to recognize a speaker at a later time. So some key parameters in our algorithm are one is how we're calculating distortion, and we did this using the Euclidean norm. And then some parameters that can be modified is how many centroids or code words are used for each training vector, what our dimension count is, which is your MFCCs, how many MFCCs you want to use in this feature space, and then a threshold on converging these centroids, which is what I'm calling a distortion change threshold. Next slide. So here is an example of a code book which has 4 centroids, and this is after we've gone through the iterative algorithm, the iterative LBG algorithm, which has converged these centroids onto the MFCC data in the feature space. Of course, we can only visualize up to 3D, so we chose 3 MFCCs to plot here, but there are higher dimensions in this code book, which are additional MFCCs. And one thing I want to point out is that this is showing the MFCC data over time, which is clustered with each centroid and it's color coordinated. Next slide. Now, ultimately, we want to compare different test vectors and find unique features such that when we run a test vector through our algorithm, we can identify which training vector best matches this test vector. So here is an example of 2 test vectors in the same 3 MFCC feature space. And you can see the red is speaker 4 and the blue is speaker 1. And this just shows the unique features between these 3 dimensions of these 3 MFCCs. Next slide. So once we have these code books trained with our training vectors, we then want to perform speaker recognition. That was our ultimate goal, right? So this is roughly similar to training, but instead of being an iterative process, we basically just go through one iteration through all of the code books where we are taking the MFCC data from our test vector. We're calculating the total distortion between all of the code books stored in our algorithm after we trained it. And we want to find who gives us the least distortion, because whoever gives us the least distortion has the code book that best defines the incoming data, which therefore is our speaker. Next slide. So that's kind of the simple way of looking at it, but you could run into issues where, say, you have 2, maybe 3 speakers that all provide the same total distortion, which is the minimum of the entire group or the entire set of code books total distortion. Well, you're not going to be very confident in which one of those 3 is the actual speaker. So we had to come up with some way to measure our confidence and to determine if we want to decide a speaker is correct or not. And the way we did this was by normalizing the total distortion over all the code books with the L infinity norm. And then we have a threshold that we set where the speaker has to exceed this threshold in order for us to determine that it is a speaker. And then we also are looking at setting a bottom threshold that the unrecognized speakers cannot exceed in order for us to say, yes, this is the correct speaker, because we don't want to have them too close. Okay, next slide. And here's an example of what our output looks like for the algorithm. We wanted to test all of our test vectors kind of in one shot and not have to run the program multiple times. And we also wanted to look at the distortion of the total distortion of each test vector to all of the code books stored in our algorithm. So this is the kind of heat map graph that we came up with, which can show us the amplitude of the total distortion for each code book of each stored code book versus our test vector. So our y-axis is test files going in. Our x-axis is all of the code books for potential predicted speakers. And when things are working normally, you want to see this x equals y type of a graph, because that means test file for speaker 1 match speaker 1 codebook, test file for speaker 2 match speaker 2 codebook, and so on and so forth. And next slide. So now I wanted to talk a little bit about the detection performance. So let's go into the first part of this is we generated multiple files with additive white Gaussian noise. And with some preliminary testing, we're able to find somewhere between 12 and 15 dB of SNR that our algorithm stops detecting at 100%, which is where things start to get more interesting. So first at 12 dB of SNR, we first tested with a 0.25% threshold exceed. So this is the speaker that we think is the correct speaker. It has to exceed 0.25, and it can only have a range of 0 to 1. And with 0.25, we had about a 72% accuracy. And then we went down to 9 dB of SNR, and you could, as you would expect with a lower SNR, our accuracy went down. But then we tried a lower prediction threshold of 0.15, and of course our accuracy, well, I shouldn't say of course, but our accuracy did go up. And the reason why it did go up is because we're using this L infinity norm to normalize the rest of our distortions that aren't the recognized speaker. And this was bringing down the likelihood of them being the speaker so low that we could set this threshold as low as 0.15 on a scale of 0 to 1. So let's go to the next slide. And then the other degraded signal that we tested were the test files going through these MEL filter banks, except we turned them into notch filters. So we would notch out certain MEL filter banks. And we went through the first 12 MEL filter banks and saw no change in our accuracy at all. Just to be clear, there is no added white noise to these files. It's just notched out frequencies. And that is it for the detection, or for the detection performance.
Okay, so now we'll do a quick demonstration of our program. So here's our main script that runs the speaker recognition. So in this script, first we read in 8 training signals. Then we extract the features of those training signals, and as a check, we try to match the signals, the testing signals against themselves to make sure that the detection works correctly. And then we read in 11 test signals, and we try to match those test signals with the training or the learned signals. And after doing some testing, by listening to the test speakers and the training speakers, we determined that each test speaker corresponds to the matching training speaker, such that training speaker 1 is test speaker 1, training speaker 2 is test speaker 2, and so forth. So we should see kind of linear prediction graph of the matches. So I'm going to run the script now. So here's a plot of training speakers matched to themselves, and as we predicted, we should match the training speakers to themselves, and that is what we see here. And then after we ran the test signals and compared them with the training or the learned data, we see that the pattern that we picked up by listening to the signals is also what this program detected. And then also for the speakers that were not in the set of the learned speakers, so that is speakers 9, 10, 11, we see that we did not have a clear prediction who the speaker is, and so we did not have a recognized speaker for those test signals. And then we also print out the results, and as you can see, speakers 9 through 11 were not recognized. And that is it for the demo.
And that's it for the presentation. Thank you.